Okay, Ireland, I am at home looking at this problem that you sent, and you might hear that squawking in the background. It's because my neighbor's got a bird. I'm sitting in the back bedroom. And you know what you have in your book here is not is not kind of the way that it's taught today. Like my textbook doesn't do exactly what this is, but I'm going to try to explain as much as I can here. Um, the first thing the thing that they mention up here, the Descartes rule of signs, that's something that we dealt with in the last video that I made for you. It would say that you're going to have no more real zeros than the number of sign changes in the terms of the polynomial function. And I think I can't see because of this thing right here, and it's a little blurred, but it looks like there was one sign change. So it means there could be one, or there could be two less than that, but there can't be two less than one. So that tells us there's one positive real zero. Then if you put in the place of x here and here, negative x, then you count the sign changes. Well, let's see. It looks like, I can't read this very well, but I think that's a 4. And that's a 2, which means when you plug in a negative x for x, it's not going to change anything, right? If you raise a negative to an even power, it's going to still be positive. So this will be a positive term, that'll be a positive, and then this will be negative. That tells you that there will be one negative real zero. Okay, so then there can't be less, right? There can't be 2 less. That would be -1. That wouldn't make sense. So this is a kind of a unique function that it has exactly one positive real zero, exactly one negative real zero. All right, now another thing that I think we talked about before, I think I included in the last video, is the rational zero theorem, or the rational zero test. And you know, the rational zero test says okay, sorry, I'm a little distracted by something going on outside at my window. This thing is being okay, there we go. The rational zero theorem says that the possible zeros that are rational numbers, that means they can be written as fractions, has to be in some way a factor of the last number divided by the first number. You know, the last number is a constant. It's 12. There's no variable. The first number has a coefficient, the first term has a coefficient of 1. So if there are any rational zeros, they have to be from the list of all the possible factors of 12 divided by all the possible factors of 1. So that's what they're making here, is this list of possible rational zeros. Now when it comes to the possible, the factors of 12, that would be 1, 2, 3, 4, 6, and 12. But if it could be 1 times 12 equals 12, then it would also be -1 times -12 equals 12. And the same thing goes for all the other numbers here. That's why these here, plus or minus 1, plus or minus 2, they're all plus or minus. You're always going to have, a possibility that the number would be a negative. So you take all the combinations of the last number divided by the first, and you come up with this finite list. I mean, there's only 1, 2, 3, 4, 5, 6. They're all plus or minus, so that's 12 possible rational zeros. Now, normally what you would do, and this is going from my book now, not the thing you sent me, is you would test those zeros, right? You would in some way, you're going to plug them in to the function here and see whether they lead to f of x equals 0. Another thing that you do sometimes is you do synthetic division in order to evaluate the function at that value. I mean, if I wanted to check to see if 1 is a possible rational zero, then I do synthetic division with 1, and I come up with the value. So I could go through this list and test them all. Now, what if none of them make f of x equal 0? What that tells you is there's no rational zeros, but there must be irrational zeros, right? There has to be two real zeros, one positive, one negative. Well, I'm talking about your function now, but that's the, if you generate a list like this, then normally what you would do is just plug them in one at a time, or use synthetic division one at a time until you found which one made f of x equal 0. But in your problem, and this is again coming from an old textbook, and maybe that's the way they did it then, they didn't do that. If you look at their function here, come on. If their function had the last number was -6, the first number was 1, so all the possible rational zeros were the factors of -6 divided by the factors of 1. Well, the factors of 6 are 1, 2, 3, and 6. And the factors of 1 are 1. So there's really not that many to check. Now notice what they did is that they didn't only check the numbers in that list. Right, here's those numbers in the list, 1, 2, 3, and 6. They started at -6, and then they checked every integer value, -6, -5, -4, -3. I mean, some of those are in this list, but not all of them. There really would be no point in checking -5 or -4 because they're not in the list. They're not going to be zeros. So they're just checking every integer value starting with -6, and they're going to go up as high as +6. But remember, they knew already from Descartes' rule of signs that there was only one real zero and one negative zero, one positive real zero, one negative real zero. Okay, well, look at the function values they get when they plug these numbers into the function, right? You can see that when x equals -2, the value of the function is +14. When x equals 0, the value of the function is, when x is -1, the value of the function is -4. So that means that somewhere in between -2 and -1, it changed sign. It went from a positive function value, that's like a y value, to a negative, which means there's a 0 somewhere in that interval. So remember, we were looking for a rational zero, or actually a real zero. It could be rational, could be irrational. Well, we're finding out here that there's a -0, but it's in between -2 and -1. That's not in this list of zeros. Okay, now they keep going. Like I said, they didn't have to check all these numbers, but they did. And when they got to +1 and +2, notice that the function values were -4 and +13. Again, if the function changed sign in between 1 and 2, that means there was a 0 in there. So that's why they stopped. I mean, I guess they could have gone up to 6 because that was the biggest number in this list, but they didn't need to because by the Descartes' rule of signs, they knew there was only one negative and one positive 0, and they'd already found them. Now what they did beyond that is it looks like they started plugging in to see if they could figure out closer, where between 1 and 2, or -1 and -2, is this 0. So they're just plugging this into the function, something for which you would need a calculator. Okay, they went 1.0, 1.1, 1.2. You can see what's going to the function values. It's not until they get up to 1.4, which is negative, and then at 1.5 the function is positive. So you know that somewhere in between those two, the function crosses the x-axis there's a 0. And it looks like they're just saying, well, if it happened there for the positive, it must have happened there with the negative. So they didn't, you don't see like they checked everything from -1 to -1.5. They're just using the -1.4 and the -1.5. And sure enough, the function changes sign at that point. So there's a 0 in there. Now, what kind of 0? Well, it's not a rational 0. Because if it was a rational 0, it would be in this list right here. So these two zeros, here and here, are irrational numbers. They have to be. Right? If I go back to my book, which again doesn't have exactly the same kind of problems that you're dealing with, but I mean, you could do some of these. This section here was really only about the rational 0 theorem. Let me see if I can. So let's take, for example, these two here. If there's any rational zeros for this function, it has to be the factors of 15 divided by the factors of 1. Right? The factors of 15 are 1, 3, 5, and 15. The factors of 1 are 1 and 1. So all the possible combinations of this number divided by the 1, which is over here, would be 15 over 1, 15 over 3, 15 over 5, 1 over 1, 3 over 1, 5 over 1, 15 over 1. And obviously they all have to be plus or minus. And you could start plugging in to see which one works, or you could do like Descartes, like they did in the example in your book. You could just like start plugging things in. I mean, how many real zeros do we expect here? Look at this. It's positive, 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 positive. How many real zeros are there? 0, right? Because if there were, they'd be changes of sign there. If I put in a negative x for x, then this term would be negative and this term would be negative. So there would be negative, positive, negative, positive. So the negative, that gives us 3 changes of sign. So there's either 3 negatives or 2 less than that, 1 negative real 0. So, you know, in our list, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, we don't really have to check the positives because there are none by Descartes' rule of signs. Okay. It looks like the problem down below is a little better. Notice they say find all the leading zeros, or find all the zeros when the leading coefficient is 1. So again, first, how many real positive real zeros? Let's see, changes of sign. 1, 2. So there could be 2 real zeros or none, right? It could be less by a factor of 2. If I put in negative values for the x and the x here, it'll change both of those signs, and then we'll have negative, 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 positive. That's 1. So we could have 2 positive real zeros, and we could have 1 negative real 0. We know that there's a total of 3 zeros. And if they're rational, meaning they look like fractions, they would have to be of the form the factors of 20 divided by the factors of 1. So here's all the factors of 20 divided by the factors of 1. So really we're only interested in, we don't need the 1 in the denominators. Now, how do they check those out? Unlike your textbook, they don't just start checking every integer value. It looks like they're using synthetic division. Sorry, I'm having trouble with my viewer here. You know, we can't see, but there's some synthetic division going on down here. Sorry about that. I'm still not the master of this tablet, I have to tell you. I mean, here's another one. Find the zeros when the leading coefficient is not 1. So if there's any rational zeros, they will be the factors of 12 divided by the factors of 10. Find all the possible combinations. So the factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 10 are 1, 2, 5, and 10. All of them will be plus or minus, and you can see their list right here. That's all the possible rational zeros. Okay, now if you look, you can see what they did next. They actually graphed it with a graphing calculator. And you can see how many zeros you see. That's 1, 2, 3, 4. So you can try to be smart about it. I mean, you could just start doing synthetic division until you get a zero out of it. You could use Descartes' law of signs. Let's see. How many changes of sign? 1, 2. So there could be 2 real zeros or there could be none. If I put in a negative for x, that'll change this sign and it'll change this sign. So it'll be positive, positive, negative, positive, 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 negative, negative. No, this is when I did the other. This positive and negative. I'm losing track. Sorry, I'm tired. Positive, positive, negative, negative, positive. That's 2 changes of sign. So there could be 2 positive and 2 negative. All right, now they've used their calculator and they've looked, and you can see there's 1, 2, 3, 4 zeros. Remember that when the graph crosses the x-axis, that means it's real. The zeros are real numbers. You don't know if they're rational numbers, but they're definitely real. And now let's see, instead of plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of these things, times 2, that's 32 different possible rational zeros. I mean, you could look at your calculator and tell. It looks like there's something in between -1 and -2, something in between -1 and 0, and something in between 3 and 4. So if you see something in this list that looks close, you could try it out. And it looks like that's what they did. There's their synthetic division. It looks like -1/2 right there. That's a 0. Okay. All right, so the factors of 3 divided by the factors of 48. If there's any rational zeros, they have to be in that list. So you just make all the zeros. Maybe you use Descartes' rule of signs. Honestly, I would graph it. And if you still have the Wabbit EMU, the emulator for the calculator, I would graph it using that. I think that's all I'm going to have time to do today. Maybe if we see each other Sunday, if there's something I can do, or maybe you can come over tomorrow or something. Just let me know. Okay, bye.